Good evening, students. This is VV Live, right? So, from Unacademy. Welcome to Unacademy YouTube classes, live classes. Unacademy yesterday started for students. Yesterday Unacademy started for EAMCET diagnosis batch. If you are a parent of EAMCET, you please subscribe. Yesterday means just 2 days before 24th December already started, and you please take plus subscription using this live VD course, right? And you're going to get benefits. All these benefits are going to get. Okay, friends, from Unacademy, you're going to provide 20 plus top educators, 10 plus batches, 250 plus courses, 2000 plus lessons, and many more every day is going to add. So to get the concession, students, you have to use live VD codes. Live VD. It's a code. It's called live VD. So this session is VD live, right? And students, now we are going to discuss about the semiconductors part 2. So we are going to discuss about semiconductors part 2. Yeah. Semiconductors, right? It's a part 2, which means lesson 2. As already discussed earlier, day before yesterday, the classification of semiconductors and how these semiconductors are classified for solids that we have seen. Apart from that, and the semiconductors are of two kinds. We know that as intrinsic semiconductors, intrinsic semiconductors and extrinsic semiconductors. And students, you know that extrinsic semiconductors are of two kinds again. What are those types of N-type semiconductors? We have likewise P-type semiconductors also we have. Fine. These are the two types of semiconductors. Now, it's time to discuss about junction diode. In this session, we are planned for junction diode. You see here it's called, it is said to be PN junction diode. It is said to be PN junction diode. Okay. In this semiconductors, semiconductor device, one of the semiconductor device is PN junction diode. Okay, here in the name itself you can see this diodes, right? Di means 2, old means electrode. Yesterday we are saying for that definition also. This 2 electrode device is made of P-type material and N-type material. So in between this P and N-type material, one junction is going to form. Now you see, here is a sample. Okay, which sample? This is a semiconductor sample. Right? Now what I am going to do is, one side, say, this side, I am going to dope this with like a pentavalent atom. Pentavalent, suppose pentavalent atom. Pentavalent atoms if I do, what happens, you know? The pentavalent atoms, when I dope with this semiconductor device, usually semiconductors are very much like silicon and germanium, as we know this one. So when we dope with this pentavalent atoms, excess number of electrons will be formed. So electrons are majority, we can see this side. And students, this side if you are doping with, right, like a trivalent. So trivalent impurity if you are taking this side, what happens here? Holes as majority we can answer. Holes as majority we can answer here. Students, are you clear with this? Now what I did is, one sample I chosen, reductor, this one, sorry, semiconductor sample either with silicon or germanium, whatever it may be. So for this pure semiconductor, or I can say this is a intrinsic semiconductor, I am doping with pentavalent one side and trivalent another side. As you know, here what happens in this case, you see, these electrons and the holes are not in equilibrium condition here. These are not equilibrium condition. So what happens here? On either side of this junction, there is a junction. On either side, these charges moves away. So right? Now that is that layer is said to be depletion layer. Now the first point before that, what you have to remind, what you have to know is one junction is forming. This junction is forming. This is said to be PN junction, right? Now whenever charges are moving away from each other from this junction, here what is going to happen? You know, here a depletion layer is going to be forming. Depletion layer means charge free region till here. Till here charge free region is going to be formed. And what happens, you see, when I say this is of electron majority, as the electron majority, I can see this is the n-type semiconductor. This is p-type semiconductor, right? So now it is electrons moves away from this positive charge. So like this, electrons moves away from the positive charge like this. So holes will repel from this negative charge, from this n-type material, from the n-type material. This is repel. So charge free region is going to be forming. This is said to be depletion layer. This is said to be depletion. Depletion means making it empty. Depletion region or layer. What we can say is a layer. Depletion layer. So now this acts as a barrier for charge carrier to cross on either side. To cross on either side, this layer or barrier, you can see this as barrier also. This barrier acts as an opposition. So to cross this junction, okay, this is the junction, this is the total barrier. Now, whenever this barrier width is less, easily charge carriers can cross on either side. When we say barrier width is more, so it offers more resistance. So that point also you have to keep in mind. So now, to cross this barrier on either side, so what we have to do is we have to give some external aid for this. External aid means like biasing. What we have to call it as biasing. So therefore, for this diode now, we are going to do for biasing. Here biasing is of two kinds. One is forward biasing. The second one is reverse bias. You see, students, this is a sample semiconductor material, right? Right here. Here is a junction. Suppose this is the junction. So this is the junction, right? Now here is the potential barrier, depletion layer. Otherwise, depletion layer. Now suppose if we are connecting positive terminal of the battery this side, negative terminal to this side. So this is p-type material. This is n-type material, for example. So in this p-type material, what are the majority charge carriers we have? Holes has majority charge carriers, and here in this electrons has majority charge carriers we can notice, right? Like this. Now you observe carefully here, whenever this p-type material is connected to positive terminal of the battery, see, negative terminal is connected to this n-type material, negative terminal of the battery is connected to n-type semiconductor material. What will happen? You just think of it. This electron, these are electrons. These electrons are negative charges, you know. So here is a negative charge. So repulsion takes place. Means electrons can cross this one. Here barrier will be there. Potential barrier. This potential barrier is different from different semiconductor materials, right? So for germanium it's of 1.3 electron volts. So easily it can cross in case of germanium. Then the 0.3 electron volts. There are 0.3 electron volts for germanium, 0.7 electron volts for silicon. So as compared to silicon, for germanium it is easy to cross. So now the point is, whenever biasing is happening like this, which means polarity is given like this, electrons can cross this one, and the holes can reach to this side also, because here is a positive plate. So like charge transfer. So holes can reach to up to this point. Holes can reach up to this point. Right? See, students, here, when electron is reaching to this region, P region, from N region to P region, here this barrier is going to be crossing. So therefore, now this diode acts like a switch that which is in on condition. So now what happens after that? Electrons are reaching to this P region and also towards this wire. along the wire. Afterwards, along the wire also this can travel. So current direction will be opposite to the direction of electrons. Electrons, if electrons move in this direction, current direction will be opposite to the electrons like this. So likewise, electrons can move through the wire like this. So current direction will be like this, opposite to the direction of electrons. Electrons are coming like this. You just see this one. Electrons are coming like this. So the direction of current will be opposite to the direction of electrons. Conventional current direction is always opposite to the direction of electrons flow. So anyhow, this total circuit is going to complete now. So it is becoming a closed circuit now. This becomes like a closed circuit. So now we can see that the passage of current in this closed circuit. Now this kind of biasing is said to be forward biasing. So current we can expect more in this kind of biasing. So what is forward biasing? Okay, for that you can say in a PN junction diode, P-type metal when connects to the positive terminal of the battery, whereas N-type metal connects to the negative terminal of the battery. The flow of charges, here charges are holes and electrons in case of semiconductor material. Mechanism is as discussed now here. Now here, in what way we discuss, like holes, how it repels to the positive plate, and when hole reaches to this point, means this N region. What happens here? One more point I have to add. When one hole reaches to this N region, here one covalent bond breaks off. Means one hole and one electron phase will be released. That electron continues the direction of the electrons, whatever present here already in it, and hole can move only in this semiconductor material. Means inside the semiconductor material due to both electrons and holes. Outside the semiconductor material due to only electrons, current is possible in case of forward bias condition. In case of forward bias condition, okay, what are the charge carriers like that? If it is asked, you have to say both electrons and holes. Both electrons and holes are charge carriers, but more clearly if they are asking inside due to the both and outside only due to the electrons, it is possible. Now in case of forward bias condition you should not, forward biasing, you should not miss the condition. P-type connects to positive terminal, N-type connects to negative terminal. See here diode symbol will be like this usually. See here, this is the diode symbol. So here this denotes P-type material, this denotes the N-type metal. We remember, this denotes the N-type material. So here this is the symbol of the diode. Diode symbol is like this. Now suppose you see students here one circuit diagram is given like this, right? Here it's given with a plus 5 volts. Here it's given with 0 volts. Diode is shown like this, and is asking whether whether diode is in forward bias or reverse bias. Reverse bias not yet discussed, but for example, if I say for this. Here, in what way you have to consider is P-type material and N-type material. In this symbol, this represents P-type material. This vertical line represents N-type material, as we know. So, this P-type metal, if it connects to high potential, plus 5 volt is greater than this 0 volts. So, that's the reason why this is in forward bias condition. Likewise, we can decide it then. Forward bias condition means P-type metal must connect to positive terminal of the battery, like that I told. This is positive terminal. Positive means what? High. This is low. Negative means low here. So high potential. P-type connects to high potential, whereas N-type connects to low potential. Low means 0. Not only in this way. Now suppose diode is shown like this for you, right? Here it's given -1. Here it's given 0 volts. So this is also in forward bias condition, isn't it? This -1 is less than this 0, no? So this also again in forward bias condition, right? And next, suppose it is given like this, right? Here it is shown like -2 volts, and it is shown like -5 volts. Now, okay, this also, here also you can see P-type connects to high potential. -2 is greater than -5. This is N-type is connected to -5. So again it is in forward bias condition. Hope you understood for the students. Very simple. P-type when it connects to high potential, N-type connects to low potential, that is forward bias condition. This forward biasing is over now. Next we will come to this reverse bias condition. Right? Coming to this reverse bias condition. Reverse bias condition. Reverse bias condition. Reverse bias. You see here, this is a semiconductor material, right? And now here is the junction. This P-type material, this is the N-type material. Biasing condition. Previously in forward bias condition, P-type connects to positive, now it connects to negative terminal. Reverse the polarity we are going to get. So now P-type connects to negative terminal of the battery, whereas N-type connects to positive terminal of the battery. See friends, what happens here? What is going to happen? Just observe here, right? Right. Here, this is the depletion layer. What actually it has initially. Now, in this, in P-type holes has majority, right? Here in N-type electrons has majority, we know that. Whenever biasing is like this, negative, the holes can attract with this negative gradient. Of course, this cannot travel through the wire, but this can move away from this junction or from this depletion layer. Whereas these electrons are having a negative charge, can be attracted, so like this electrons can be. So from the depletion layer like this, these charge carriers move away. Means depletion layer width can increase in reverse bias condition. So resistance will increase. As resistance increases, current decreases. Right? Here in this case, forward bias condition, what happens? Here, whenever this width, charge carriers are moving like this, this width will decrease like this. So then that time resistance decreases and the current value increases. According to V is equals to, according to that relation between resistance and current. Of course, like in ohms, like in metals, it cannot obey Ohm's law. Semiconductors cannot obey Ohm's law, but still the relation follows. Resistance and current relation is inversely proportional only. So therefore here, whenever this depletion layer will increases, the resistance will increase and the current will decrease. So this is the reverse bias condition. In this also, again you see. Now you can say, sir, what about current in this reverse bias condition? Whether it is zero or something else? Yes, something else. Somewhat current will be produced here. Due to what, sir? Further time. Here, holes have majority, but electrons are also present. Electrons are minority here. Minority means less in number. Here holes are minority, less in number, that's it. Less number. But if you observe this charges of these electrons and negative repulse, so this can cross for this. So holes positive. So this can cross. So here, due to minority charge carriers, you have to note this one. This due to due to minority charge carriers. What I'm saying is minority, which means just less in number. Minority charge carriers will contribute to current, and also as this potential increases here. So here potential will be there, barrier potential. This barrier potential value when we are increasing means from this battery we are going to supply that. When we are increasing the potential, when we are going to supply this energy, so what happens? Potential. Here charges are there, electrons and holes. These electrons here in this in this region, electrons have minority. This is the P-type material. So minority charge carriers are the electrons. These electrons can collide with the covalent bonds. In the covalent bonds, what are present? Electron and hole. Hole is with positive charge, electron with negative charge. So that the pair of electron and hole will be released when this electron is going to collide with the atom. So therefore, what happens, again in this electron and the hole pair, when it releases, okay, the released electrons will collide with the remaining atoms of the semiconductor material. Therefore, like one flood, this electrons number will increase, right? So therefore, suddenly current will saturate, and this will appear in microamperes range. So likewise, even in the reverse bias condition, current is possible. So that the corresponding potential is said to be, okay, that voltage is said to be, okay, avalanche voltage, right? Here in this forward bias condition, okay, that voltage at which this current will start is said to be knee voltage, okay, knee voltage, okay, okay. Likewise, here we can compare both of these two. Students, you can see here, in this reverse bias condition, in microampere range, currents can be obtained, whereas in this forward bias condition, currents will be obtained in milliamperes range. Okay, in milliamperes range. As you know, milli means 10 power minus 3. Okay, amperes. Here, micro means, okay, 10 power minus 6 amperes range. Right? Here it is due to minority charge carrier. It is due to minority charge carrier. Likewise, reverse bias. Now you see for this reverse bias condition, for example, problems if you see. Here suppose minus 2 volts is there. Right? Here this of p-type metal, this of n-type metal, students. Suppose if it wants to be in reverse bias condition, p-type connects to negative. This connects to positive, minus 1 volt. So minus 1 is greater than minus 2. So p-type is low potential, is at a low potential. N-type is at a high potential. Whether minus 1, 0 volt, 1 volt, you can write all of these values. So this will be in reverse bias condition in that case. And next, suppose you see, here is a diode like this, right? It's grounded. So N-type connects to 0 volt, ground means 0 volt. P-type connects to, right? Okay, minus 5 volt. What I am saying is minus 5 volt. So whenever it is connected, connection is given like this, right? This diode circuit connection is given like this. This N-type is connected to high voltage, whereas P-type connects to low voltage since it is minus 5. So this diode is in reverse bias condition. This diode is in reverse bias condition. In reverse bias condition, how it acts? It acts like off switch. Switch is in off condition, whereas in forward bias condition, it acts like a on switch. Switch is in on condition. This point you should know. So likewise, we have forward bias and the reverse bias conditions of a diode. In these two biasing conditions, okay, electricity means current is possible. But of course, in forward bias condition, milliamperes range. In reverse bias condition, okay, it appears in microamperes range. And we have seen the mechanism, flow of charges mechanism we have discussed. Okay, you should remember for all of this. Very simple things we have discussed actually today. PN junction diode. PN junction diode is nothing but it is a semiconductor device which is made from p-type metal and n-type material. Okay, how to get p-type metal and n-type material? To prepare p-type material, trivalent impurity is to be added to the pure semiconductor like this. Hole pass majority. N-type semiconductor means electron pass majority. Pentavalent atoms to be added to the pure semiconductor. Likewise, we can get. And now, thereafter, what is happening? This depletion layer is going to be forming. So, whenever depletion is making it empty. So, free space region. This is said to be free space region. So, this acts like a barrier for charge carriers on either side. To cause this barrier, we are going for biasing. So, biasing is of two kinds. Here, you have to concentrate on this. Here, this is depletion layer. As depletion layer width increases, the resistance will increase. Current value will decrease. Okay, barrier potential. Okay, barrier potential will increase if this width is increasing. If this width is less, barrier potential will decrease. So easily charge carriers can cross on either side. So biasing. So to cross that barrier or charge carriers on either side, we are going to bias the diode. Biasing is nothing but just giving the external aid, means battery supply we are giving. When we are giving battery supply, if we follow these conditions, like when p-type metal connects to n-type, p-type metal connects to positive plate of the battery and the n-type metal connects to negative plate of the battery, we have seen the mechanism, how charges are repelling or attracting. These holes in p-type holes are majority charge carriers. This can attract towards this positive plate, but till this sample only this can reach. This hole can reach till this sample only, because hole is nothing but lack of electron in covalent bond of a semiconductor material. So inside the semiconductor material only hole can contribute its current, its charge, right? So therefore, now when we think of this electrons, when electron is okay subjected to this negative plate, these electrons can repel. Can repel means towards this p region, these electrons will travel. This can move. So therefore, here what is happening? This barrier is going to cross. So now this barrier is going off. So therefore, charge carriers are easily able to cross on each other. So current is positive. Now these electrons can easily attract towards this positive plate and can complete the closed circuit via this external wire. So in this, inside the sample the semiconductor material, both electrons and holes are contributing current. Outside, just due to the electrons, current is possible. Likewise, we can see. And now, if you are choosing for germanium as a PN junction diode material, it requires just 0.3 electron volts here, barrier potential. If you are going for silicon, it requires bit more 0.7 electron volts. So here supplying potential minus this potential is the resulting potential while we are calculating the current. I is equals to V by R basically. So for that. And here in case of forward bias condition, it is okay. This diode acts like a closed. Okay, this acts like a closed switch. Means switch is in on condition. Means current is passing. So that's the reason. Now generally this is the symbol for the diode. This is the symbol for diode. Here this one. This vertical line represents n-type metal. This section represents p-type metal. So example problems we have seen. In this all, p-type when connects to high potential, that is that is p-type connects to high potential, n-type connects to low potential, that is forward bias condition, and coming to reverse bias condition. Here you see, in case of reverse bias condition, p-type connects to negative plate. So therefore, holes can repel till here. These electrons can move up to here. When hole is reaching to this region, okay, electron, okay. So what is that? Generally, this hole cannot be moved not towards this, right? Because this is having positive charge, this is negative plate. It is supplied with negative plate, so it moves away. So here, minority charge carrier, like electrons in this p-type material, holes in this n-type material, can able to cross this because the electrons is negative plate, so this becomes due to like charges, this electron can repulse and easily cross it. So likewise, even holes also. So likewise, here due to this minority charge carriers, and also when one electron is going to hit the atom, okay, covalent bond, when it is going to hit a covalent bond will breaks up and electron and hole pair can be released. Electron and hole pair can be released. So again, what happens? Hole can move, can able to move in this, but electron, okay, able to travel in this wire. So like this, current is possible. So here a simple diagram is there. Diagram is but one graph is there. Okay. So this is the voltage axis. This is the current axis. So for forward bias like this, and for reverse bias you see like this. So this voltage is said to be knee voltage. This voltage is said to be knee voltage. This voltage is said to be avalanche voltage. Whenever these electrons are going to collide with the atoms, then covalent bonds will break off. So like a flood, current will increase, and it is in order of microampere. Whereas in this this becomes milliampere phase. This is of forward bias condition case, this is of reverse bias condition case. You see, in reverse bias condition, even though we are increasing for the potential, this current is not having appreciable change. At one particular potential called avalanche potential or breakdown voltage, we can call this as breakdown voltage. Okay, current saturates in microampere range, whereas this is very clear. At the knee voltage, this current saturates, right? So this is the topic, friends. Hope you are all understood, right? And thank you for listening, right? I'm closing for this.